Hi everyone, welcome to Math 244 Snow Day Edition. So this is going to be what we're going to have to do on account of the weather conditions out there. I hope everyone is staying warm and safe and staying off the roads. And here we're just going to sit back, relax, and let our calculators do some of the hard work for us while we sip our hot chocolate. So here we go. What we're going to talk about is 9.5, 9.6, where we'll just quickly see how to make a TI-84 do some of our work for us. And that work in question will be confidence intervals and hypothesis tests, because they are both very similar. Confidence intervals and hypothesis tests on calculators, specifically TI-84 style. So there are a couple other kinds of calculators that can do pretty much the exact same things as TI-84 and in the exact same way. So if you have a TI-84 or a highly related calculator, it will all go very similarly to what I'm about to demonstrate. Okay, so first off, where do you do any of your statistics in a TI-84? It's under the Stat button. So if you look at the Stat button, right here, when you press that, it opens up. Show what it looks like. It opens up these three options: edit, calculate, or tests. So specifically, we will or won't use the edit depending on the nature of the information given to us. So edit is what you use if the problems that you're trying to work out give you a list of actual data values instead of giving you the summary statistics. So, so this is used data values when given. And then once you have the data values, if appropriate, once you have them entered in, that's when you can start doing some of the tests. So let's see what tests there are and see what we can guess about each one. Okay, so taking a quick look here. Go do tests. All right, tests is now selected, and here we have a bunch of options, and they all are starting to make a little bit of sense. At least some of them, anyway. We have a z-test, a t-test, and these ones we'll learn about shortly. And then down here we have a one proportion z-test. And then on the subject of intervals, we've got a z-interval, a t-interval, and a one proportion z-interval. By the way, as this class progresses, we will learn actually just about all of the tests that are on here. So all these intimidating looking tests will be things that we will learn how to use in the days and weeks ahead. Anyway, so let's explore the ones that are currently in our capacity. So first off, the z-test. So this is specifically for a mean, and it's the occasion when you use a z-test for a mean, which is the occasion where you have a standard deviation given to you. So this is a test for a mean with sigma given, standard deviation given. Versus, on the other hand, a t-test. So this is the test for a mean again. With no sigma given. Okay. We have a 1 proportion z-test. And this is a z-test for a proportion. And then while we're at it, just on that very same little menu, just a little bit further down, we also have the confidence intervals, which can go z interval, so this is a confidence interval, again, using the z distribution. It's a confidence interval where sigma is given, and then we have a t interval, confidence interval for a mean. Oops. And then there's the t interval, which is also for a mean. For mean, no sigma given. And then lastly, we have the confidence interval for a proportion, which was called 1 proportion z interval. All right, so this is confidence interval for proportions. Okay. Now, within each of these options, well, most specifically for the means, we will be given a choice of either entering in the statistics of the situation or the individual data values directly. So specifically, stats versus data. So to see as an example, go to a t-test. This is an example. We have stats or data as our options. And specifically, the difference between these is use. This one is what you use to put in the actual data values. Oops. Use the values on a list. Versus stats, where you just give it the summary statistics. Okay, and then you've got all the things that you need to add to fill in on each of them, and hopefully they will all make some sense. And then at the very bottom, there is calculate. Calculate versus draw. So calculating will just tell you things like the test statistic, the p-value, and things of that sort, just letting you draw your conclusion. Draw, this is again for this is for tests specifically, that will give you the actual bell curve with the appropriate piece shaded as matches your tails of your hypothesis test. So this just gives you the information you need to make a conclusion. So this just performs the test. And this shows the bell curve. Okay, well, let's actually try doing this in each of the types of situations that we will frequently encounter in this part of this course. So what I'm about to switch over to now is the worksheet that we have for this little installment, and this can be found on Canvas. So here we go. Let's have a look at the first scenario, which involves Marco, a quarterback, and how far he can throw a football. So specifically, sorry, this is a updated version of it. So specifically, here is the deal. Ordinarily, the mean throwing distance for Marco is 40 yards. And the standard deviation, which we are told is a population standard deviation. Ordinarily, whenever we are told just a standard deviation in general and no specific sample is given for us, that will mean that it is the population standard deviation, whether it says it or not. But in any case, so now we are looking at a mean, we are looking at a standard deviation. And the team coach tells Marco to adjust his grip to get more distance. So now Marco adjusts his grip, and he throws the ball 20 more times, and the coach records those distances. For the 20 throws, Marco's mean distance is now 41.5 yards. So the coach thought the different grip helped Marco throw farther than the 40 yards. Assume the throw distances for footballs are normal. All right, well that's good news because that gets us out of the pickle of having slightly too small of a sample size. So 20 is not a bad sample size, but it's not ideal either. You would like ideally to be at least 30. But it can be we can get out of this by having an assumed normal distribution to begin with. So first off, if we are going to be talking about this situation, all of this is going to be using a z-test or a z-interval. Okay. So just good to note. So if we want the confidence interval here, and whenever you're in some weird thing, you can just do a second and quit to get yourself back to a regular screen here. And so now, what do I want to do? I want to go over to tests here and find ourselves an interval for the confidence interval. So we go to z-interval. Now we have a choice of data or stats. They haven't given us the numbers of the 20 individual throws here, so we switch it to stats. So that means we are told now the or we're given now an opportunity to fill in the specific ingredients for each situation. So here, it's just going to be a standard deviation of 2, it looks like. Looks like our new population mean is 41.5. The population size, the sample size, I mean, is 20. We got a sample all of our sample things in here, along with the population standard deviation. And then we just set our confidence level as the problem dictates. By default, a confidence level of 95 would be standard, but here it says specifically 99%. So we will obey that. And then we just calculate. And here we just have the answer just right there. So it's 40.348 on the low end, 42.652 on the higher end. So the coach thought that the grip would cause Marco's distance to be longer than it was before, and based on these 20 throws, we can say with 99% confidence that Marco's mean throwing distance now is somewhere between these two values. Nice to know. Nice to know. Was that significant? Well, let's figure it out. So we want to do a hypothesis test. We have to make some decisions here. First off, we have to nail down for sure what are the null and the alternative hypotheses. So the null hypothesis is that nothing is different here. Everything is what you thought. It used to be a mean of 40. It's still a mean of 40. Okay, now the alternative. So if the coach is right, then the mean is not going to be 40 anymore now that Marco is using a new grip. The mean is supposed to be bigger than 40. So we know it's going to be a one-tailed test. Okay, well, is it a z distribution or a t distribution? Well, it's still going to be a z test. Because sigma is still given to us. So here we go. Just hit stat, back to here, and away we go. So we'll go, fit everything. We'll go over to tests. And a t-test. Sorry, a z-test, I mean. Z-test. So stats versus data again. Well, we still just actually have the we have the process statistics here, not the raw data. So we will just enter the things as they fit. So this mu represents the null parameter. So it's the parameter that that the null hypothesis says that it equals. Here we have the sigma and the x bar from before. The nice thing about these tests is if you do it on one end with the confidence interval, it will save as much of that information as possible, so you can immediately do a hypothesis test with the same values. Okay, and so these things are all the same. Now here, if it's a hypothesis test, we have to decide on our hypothesis. And so either two-tailed, left-tailed, or right-tailed. So specifically here, we are looking at the right-tailed one. And let's just start by calculating it and see what we get. All right, what does it want? It wants the p-value. And here, just a note on this. So this is being given in scientific notation because the number is so small. We can't waste the space on the calculator just listing all of the extra digits on it. So specifically, what that means is, remember, take the 3.98. 398. Decimal place was right here. So move it 4 notches over 1, 2, 3, 4. So that means 0, 0, 0. So 0.000. More clear. 3 zeros and then 398. Okay, in other words, very tiny. Very tiny. So the p-value here is way less than 0.01. 0.01 would be right here. So we're expecting to be looking at something that is going to be only the tiniest little sliver of a bell curve. Now, how tiny a sliver in the bell curve will it be? Go to stat, go to tests, just go to the exact test we just did, the z-test. And all of the values that we already entered are still there, still good. And now instead of doing calculate, do draw. And then it takes it a minute here, but here it goes. System processing. System processing. And here comes a bell curve with a teeny tiny little sliver off to the side there. And actually it tells you even what the z score was. So that's going to be, so our z value is just a tiny little corner over here. Okay. All right, well, now we state a conclusion in context. That does not mean just say straight up reject null or fail to reject null, but we say something about Marco and his prospects on the football field. So here specifically, so just we'll note that this is going to be a rejection of the null hypothesis, which is, for Marco's case, good news. It means that the coach's adjustment to his grip has actually had a significant effect on Marco's distance. So in context, the new grip produces a higher mean with significance at the 1% level. There are a number of ways you can word it, but that'd be one of them. At the 1% level. Okay. Anyway, word it however you want to word it. Just make sure you get something in there about 1% and statistically significantly higher. Okay. Let's now talk about some students from PSU taking a geography test. So the national average on this particular test is told to us to be 65. We want to see whether the PSU scores are different. Is different from 65. So the national average on this test. So here are the data values that we have from our little sample of 10 values. Sure enough, count them up. 10. Good. Okay, so based on the information that has been told and the information that hasn't, we now see that this is going to have to be a t-test, or a t-distribution. So t-interval, t-test, because we are not told anything about the standard deviation. Okay, so it's a t-distribution, and we'll just go straight for the confidence interval. Notice the confidence level is now 95%. So we'll just put in the values that we have here. So here's how you put in values when they are given to you in a list format like this. So you can just use quit or just hit that right away. And since we want to enter the values, we go to edit, and that takes us to a list format. Now, if the values that are in the list are not the ones you want, these ones happen to be, but they won't usually be. Here's the easiest way to quickly clear them. You go up to the top here, up to the very top, and you do clear, enter. clear enter. Not delete. Not delete. Never hit delete. If you hit delete, you're gonna have to reset your calculator if you want it to ever look good again. Instead, it is clear enter. Clear. Not delete. Clear. Okay. So anyway, once we have cleared away any pre-existing values, we start entering our new ones. 65, 65, 70, 67. And then what do we have? 66, 63, 68, 72, and 71. So then you quickly make sure that everything is good, you didn't miss anything. And I must have missed one because I only have 9 values here. So quickly look over it. 65, 65, 70, 67, 66, 63. Okay, I needed another 63. That was it. So one way you can tell if you missed one like I just did, which is a thing that can happen to us all, is it tells you what entry you're on down in the part right here. So it says list 1, item number 10 equals this. So that's what told me that I only had 9 values instead of the 10 that I'm supposed to. Once you've entered your values in there though, and if you've done it correctly, then you are ready to proceed, and you go to set, tests. First, we are looking at an interval, not a z-interval, because we don't have a standard deviation to enter, but a t-interval. Now hit enter, and then once again, it needs to know what are you entering, the statistics information or the raw data. In this case, it's raw data. By the way, right here, it asks you what list you want to draw from. If you actually did have these values in a different list, not list 1, the way you can tell the calculator that is right here in the same button where it says stat, go to second and list, and you find the list in question. Like let's say your data was actually in list 4. So then you hit enter and it would be list 4. But that is not the case here. So we'll go back to list 1. So you go up and down until you find the list in question and enter. And once you have that, then you're good. As for frequency, that's what that one stands for. What this represents is a situation where you have your data values listed along with their relative frequencies. So instead of being a raw list of literally every individual number, it would be, say, like 65, and then another list that tells you how many times 65 appears. But we won't be doing that right now, so keep frequency just at 1. Confidence level, need to update that to the confidence interval in this case, which is 95%. And once everything is there, we hit enter and we are good to go. Once again, the confidence interval just comes right on up. So, reading the confidence interval off of the output here, we have 64. Paper's not big enough for everything here. We've got 64 point, 64, 0.713 to 69.287. Okay, so with 95% confidence, we can say that the mean score of a PSU student is somewhere between here and here. So if I wanted to give a sentence that interprets that, that is the sentence I would give. I would say with 95% confidence. The mean PSU student score is between 64.713 and 69.287. If the problem had asked us to interpret it, that's the kind of sentence we would write. Okay, now, now we are about to actually figure out, is the difference actually significant between the PSU students here and the nation as a whole? So once again, we will run to the calculator to give us the answers. So specifically, you just go stat again, tests. And now it is a t-test. The input is coming from the data, and it wants to know what is the null hypothesis here. Okay, so let's quickly figure that out. So the null hypothesis in this case is going to be whether the mean for PSU is the same or not the same as the national average. And the national average was 65. So if there's no difference, then 65 was the mean of the nation as a whole. It will be the mean of PSU students as well. Here it just says different from, so that just means we are talking about the two-tailed, not greater than, not less than, but either way. Okay, and this is a t-test as usual, or sorry, as the confidence interval also was. Okay. Now, what are the things we need? The p-value, the position of our test statistic, and a conclusion. So, going down the items here, all very much the same, except unlike the confidence interval, we do need to state which direction we are talking about here. So, is it two-tailed? Is it left-tailed? Is it right-tailed? This time it shall be two-tailed. And we'll calculate. So here, oops, I forgot to change my mean. So change the mean now to 65. Okay. Now everything is fine. Here we go. Okay, so what do we get here? We got a p-value of 0.079. 3 just in case I wanted the extra digit there. But our significance level was 0.05. This is not below that, so therefore we don't reject the null hypothesis. So what does that mean? That means that PSU students are not statistically significantly different from the national average based on this this little sample. So PSU students in this sample were not significantly different. From the national average. And again, if I don't say the significance level, then one can assume that I probably mean 5. And here, just to be extra careful, we should say the mean of PSU students in the sample. I guess that means this now has to be was not. So if we're saying that something is or is not statistically significantly different from something else, It's good to be precise about what actual statistics thing we're talking about here. And in this case, it would be the mean. Okay, well, let's keep the party going. What else we have here? Let's talk about married couples. So we want to test whether the percentage of couples who got married in 2023 with an age gap of at least 10 years is more than 8%. So maybe it was 8% the year before, and we now want to see, has that number increased? Has it decreased? What is the situation? So here we are talking about percentage. So percentage means proportion. Proportions are always going to be z distributions. Okay. Well, here we go. And now let's just have a look at what the proportion side of things look like in the statistics menu. So you go once again, statistics. Statistics. Go over to tests. Find yourself a one proportion z-test. So there it is. And now what you need to enter are the specifics of this particular situation. Oops, sorry, we're not doing a test yet. We're going to do an interval first. And we want a one proportion z interval. So on a lot of these we have one proportions or two proportion options. Make sure you pick the one proportion here. And what do we have here? So specifically the n represents the 200, and the x is the 20. So rather than it asking us for the proportion as a whole, it just asks us what the raw number of yeses was in this particular case. So 20 yeses out of 200 people, and then the calculator will take it from there. Once again, we've got a different confidence interval now, or confidence level now, I should say. So specifically 90%. Whenever you're doing something where it's just kind of for fun, it's typical to make the confidence level a little less, so that you can just investigate something, just something kind of uh, pop sciencey, like age gaps in marriage. This would be the kind of thing that you would expect to see in a Slate.com piece or something like that. It's not a matter for Scientific American, just a matter for fun. So whenever that's the case, that will be the times when you will most likely adjust the confidence level downward. It is not so important as before to avoid a type 1 error if it's just for fun. Okay, so once again, here we go. So here's our confidence interval. Just look at the numbers, 0.465. Oh, I didn't update any of that information. I didn't enter any of the information here. I just got talking about Slate and stuff, and forgot to actually put in the actual things. So one proportion z interval. Okay. So what was the x in this case? It was a mere 20 out of 200. Okay. Here we go. Okay, correct confidence interval 0.06511 to 0. The calculator doesn't put the 0 before the decimal point, but it's a good idea to put it so as to make it clearer, easier to read. So 13.4, 0.13489. Now, if you want to interpret something like this, then it is time to change that back from a decimal to a percent. So between so change it to a percent, so move the decimal spot 2 over. It'll be 6.511%. and 13.489. Of couples, and I should say newly married couples, newlywed couples, have a 10+ year age gap. Oops. All right, but let's actually do the test now. That's what we really want. And this was, again, 10% confidence on this. The confidence level you use when you're just doing something for fun. Okay, hypothesis test at the alpha equals 0.10. So that's the corresponding significance level for that confidence level. Okay, now we look at the situation again and make our decisions about the null and the alternative hypotheses. So it says we want to test whether the age gap couples are more than 8% of the population. That means we're comparing it with 0.08, so that's the null, and then the alternative is it's greater than that. By the way, the information that the confidence interval on the calculator gives you does also include the sample proportion. So just as a note, we thought that it was going to be more than 8%, and in fact, this particular sample had 10%. Is that difference significant? Is it not? Who's to say? Oh, we didn't sketch the last one, did we? Let's go quickly back to the last one. We forgot to sketch the position on the bell curve. So here specifically, so going back to these PSU students, so the data should all still be fresh in the calculator since we haven't made any adjustments on a t-test. So we got a bell curve here. So let's just go back to the t-test. So it's a t-test. Beep. Still using L1, still using all these same things, and we draw. And here comes your system processing. System processing. System processing. You really make your calculator work for it on these when you're asking it to draw. All right, there we go. So now there's our bell curve, and we can see it was a two-tailed hypothesis, and that means that we've got the two shaded pieces over here and over here. And the t in this case was 1.978, which is on the right side. So it's a two-tailed hypothesis, so that means we have both tails in effect, but our t happened to be on the right side. You can tell because it's positive. Okay. All right. Sorry for that interruption. We just want to make sure we tie up all the loose ends. Okay, back to this one now. We are talking about a proportion. So this is going to be a z-test. Z-distribution for proportion. There's a one proportion z-test here. Okay, now what's the null hypothesis? It is supposed to be 0.08. What are our x values and n values? The same as before. What was our tail situation? Says more than. So switch it over to greater than. Calculate. So our p-value now 0.14857. We don't. Bigger than 10%, so we don't reject. Not. And now this time I'll remember. I actually put it in the bell curve here. So just go back to stat, go back to tests. And by the way, if you can see which one it is that you want, you can just type the number too. You don't have to actually scroll down each time. So here it's going to be 5 is the option we're looking for. And then you go down, go to draw. And sure enough, we have a pretty big shaded area on this one. So that's going to be our Z. Right there. Okay, well, our conclusion, no conclusion. So our samples proportion of newlyweds with 10 or more year age gaps was not significantly different from 8% at the 10% significance level. And that's what significantly means here, is with that level of significance, the difference was not significant. Okay. All right. So that last one was a situation that is just for fun. And so a lower confidence level was able to be used. Here, we are going to look at cell phone users and brain cancer. So, a study of a lot of cell phone users, so more than 400,000. We had 172 of the subjects from that study developed brain cancer. So we want to test the claim that cell phone users developed brain cancer at a greater rate than that for non-cell phone users. And for non-cell phone users, whoever those people are, apparently the rate is this. So 0.0341. And because this one is not a joking matter, this one is serious, we're talking about brain cancer here, we have to make sure to tighten the screws a little bit. So make it a little bit stricter. So that means lower significance level, higher confidence level. Okay. Well, in any case, this is again proportion, so this is going to be a z distribution. And we'll go straight for the confidence interval to begin with. So stat. Tests. One proportion confidence interval. There it is. Okay, what do we got here? We have 172 confirmed cases in this. We have 420,000 is 1019 as our sample size, and our confidence level has to be 0.995. Okay, so what is our confidence interval here? It is 3.2 times 10 to the negative fourth. Remember scientific notation here. To, looks like 5 times 10 to the negative fourth. So if I want to change each of these out of scientific notation into regular notation, I would take their decimal point and move it the appropriate number of spots. So it's going to be whoop, 1, 2, 3, 4. And then you put in zeros in each of the little spots that you've opened up there. So that means 0, 0, 0, 3, 2. And this one will be the same number of zeros, 0, 0, 0, 5. The problem asks us about it as a percent. So now we have to do like the double conversion here. We changed it from scientific notation to regular notation. And now regular notation to percent. Move the decimal spot 2 notches back the other way. So roop, roop. That means 0.032% to 2 notches over. So that's going to be 0. Now it's just going to be 0.05%. Well. If we look at the rate of the public as a whole, it appears to be slight, or just right on the tail, on the left tail of this interval. Well, what does that mean as far as a significance test? As far as a significance level and a hypothesis test? Well, let's just crunch the numbers and find out. So, null alternative. Talking about a proportion here. So, whoop, whoop, whoop. 3, 4, 0. So proportions, you can make it a percent. That wouldn't be terrible, but it's better to just put it in as a decimal. It says greater rate, so that means P is supposed to be in an alternative hypothesis. Fit everything in here. Okay, so P is going to be greater than 2, 3, 3, 4, oh. All right. Well, p-value and then the sketch as usual. So, all right, we got the interval. Now we do the test. So it's a one proportion t-test, or z-test, I mean, and information of interest is mostly filled in. We need to update the null hypothesis here to be 0.00034. Notice it automatically changed it to scientific notation. If you yourself wanted to put it in scientific notation, you can do 3.4. And then the way to do that E is right here. It's the button right above 7. So you do second and E and -4. Make sure whenever you're doing a negative on a calculator, you use the negative button, not the subtract button. That will lead to an error. But in any case, you enter it, and see it accepts it that way as well. Calculate. So tails, yeah, right tail. Good. So calculate. P-value 0.00727. I gotta round it somewhere. Might as well round it there. Okay. So by the way, that means we are not rejecting the null hypothesis. Interesting. So, keeping on going, we need the bell curve now. So back to tests, back to one sample proportion. Sorry, one proportion z-test. So number 5, and everything's the same except go over to draw rather than calculate. And what have we got here? What have we got? There's our precious bell curve, and you can see it's just shaded a bit on the right. Tiny little piece over here. And this was a Z distribution, so it's going to be a Z. And the calculator says Z is 2.4434. Which is going to be on the right because it's positive, as we can see. All right, we did not reject the null hypothesis. What that means is basically that there was not statistically significant evidence. So, not at that level anyway. The proportion of cell users in our sample who developed brain cancer was not significantly different from non-cell users. And by significant, we mean at the 0.5, not 5% like usual, but even tighter. Significance level. Why did we use such a strict significance level again? Well, if we want to do something important like test for things that might cause cancer, we want to be as sure as we can be in our conclusion. And the significance level, you remember, is also the probability, if the null hypothesis is actually true, of accidentally rejecting it anyway. So that's a type 1 error. So specifically, significance level is the same as the probability of a type 1 error. We want to minimize this so we don't accidentally think that cell phones cause, alpha is the probability of a type 1 error. We want to make this as small as possible so that we don't accidentally think that there is a statistically significant link between cell phones and cancer if there isn't. So we don't want to accidentally conclude that cell phones cause cancer if they don't. If it isn't true. So that's why we want to be strict on this one. For this other one, it was a lighter topic, so we could, it's just about May, December romances, that kind of thing. It is not it's not something that has life and death stakes attached to it, so we can afford to be more playful in our significance level. In any case, I think that just about will cover it for now. So the most important thing here is to remember where on your calculator you can find all the statistics stuff. all under stat. If you don't yet have your calculator, now you see you are going to be needing it. And this is also going to be true for the homework, which you can now do from chapter 9 for hypothesis tests of means and hypothesis tests of proportions. So you can now finish the homework on Canvas from chapter 9. Also, to remind everyone, there is a quiz. It is a take-home quiz this week because of the unusual circumstances. However, ordinarily there will be, it'll just be an in-person quiz happening on Thursdays. The only reason that might change is if we need to make up some lost time from the classes that got canceled. In any case, thank you for joining me for this episode of Math 244, the Snow Day edition. All right, I will hopefully be seeing you all next week in actual person, but until then, stay warm, stay safe, stay indoors. All right, see you next week.